Welcome to the Pro Ticker Deep Dive.
It's great to be here.
I was just looking at the calendar this morning, and it hit me. We're in early February 2026.
It doesn't feel real, does it?
It really doesn't. And I had this sort of whiplash moment. Do you remember where the industry was, say, 5 years ago? I mean, even 3 years ago?
Oh, absolutely. It's a different planet.
Right. It feels like we've packed a solid decade of evolution, maybe more, into just the last 18 months.
That's not an exaggeration. If you rewind the clock to, 2023, maybe early 2024, the entire conversation was about potential. It was all theory.
It was the imagine what AI could do era.
Exactly. Every keynote was about imagination. But sitting here today in 2026, that whole tone, that whole narrative has just completely shifted. We're not imagining anymore.
No, we are building.
We are building. The hype phase is officially in the rearview mirror, and we are deep in the deployment phase.
And deployment is messy.
Messy is a good word for it. It's also incredibly expensive. And it's physically massive. I mean, we are looking at a global chip market that is just barreling toward $1 trillion in annual sales.
$1 trillion. I want to just pause on that number for a second.
It's hard to wrap your head around.
It is, because if you just read that headline, chip market hits $1 trillion milestone, it sounds like a huge party. It sounds like everyone is winning.
Right, a rising tide lifts all boats.
But when I was digging through the stack of research for this dive, the vibe I got wasn't a party at all. It was more like, I don't know, anxiety. Or maybe a very, very high-stakes poker game where, half the table is winning everything and the other half is just folding hand after hand.
That is a perfect description. The headline number, that $1 trillion, it hides a much more complicated reality.
Which is?
It's what you could call a split-screen economy. If you look at the industry right now, it's two different worlds. On the left side of your screen, you have AI data center infrastructure.
And that chart is just a vertical line going up.
A vertical line. It's breaking records every single quarter. It's an absolutely insatiable beast that's just consuming capital and capacity.
Okay, so that's the left side of the screen. What's on the right?
On the right side, you have everything else. You have the things that normal people actually go out and buy.
Smartphones, laptops.
Personal computers, automotive chips, industrial sensors. That side of the screen is, well, the polite term is stabilizing.
Stabilizing. That sounds like a word an executive uses when they don't want to say flat.
It's not crashing, let's be clear.
Yeah.
But it is absolutely not booming. It's just muddling through. It's a completely different story.
And this split-screen reality, it leads to these statistics that just, they don't feel like they can be true. There was one stat in the notes that I honestly thought was a typo. I circled it.
I think I know what you're talking about.
It says here that in 2026, this year, high-value AI chips, so, the NVIDIA Blackwells, the AMD MI450s, they're projected to drive roughly 50% of total industry revenue.
That's correct. Half.
Half of the $1 trillion. Half $1 trillion from this one segment. But, and this is the part that completely breaks my brain, those exact same chips represent less than 0.2% of the total volume of chips produced.
It's a staggering disconnect, isn't it?
It seems mathematically impossible. How can 0.2% of the widgets you sell generate 50% of the cash? It makes no sense.
It's all about value density.
It's like a grocery store making half its annual profit selling, 3 bottles of incredibly expensive wine while selling millions of loaves of bread at cost.
That's not a bad analogy, actually. But let's sharpen a little bit. Let's use a car dealership.
Right.
Imagine a dealership that sells 10,000 cars a year. Now, 9,980 of them are budget sedans, your reliable commodity transport. They have low margins. They're volume sellers. They keep the lights on.
Right, the bread and butter.
Exactly. But then 20 of those cars they sell are custom built.
Yeah.
Formula One grade hypercars that cost $10 million each.
And the hypercars are the AI GPUs.
Precisely. The value is just on a different plane of existence. A single finished wafer of H100 or Blackwell chips is worth more than a luxury home.
Wow.
Meanwhile, a wafer of, say, power management chips for a toaster is worth, well, a toaster. The industry is effectively bifurcated. You have the commodity tier and you have the strategic tier, and that strategic tier is just sucking all of the oxygen out of the room.
And oxygen in this case is a metaphor for capital, for talent, and maybe most importantly, for manufacturing capacity.
And that is the risk. That is the so what for everyone listening who doesn't run a hedge fund or work at a hyperscaler. This isn't just some Wall Street curiosity.
No, this has real-world consequences.
This concentration creates a massive, massive vulnerability in the entire global supply chain. Because manufacturing capacity, the clean rooms, the EUV lithography machines, the advanced packaging facilities, it's finite. There's only so much to go around. It's a zero-sum game.
So if I'm a big foundry, like a TSMC or a Samsung, and I had a limited amount of floor space, am I going to use that precious space to build the toaster chip or the hypercar chip?
You build the hypercar chip. Every single time. The margins are astronomical. It's not even a question.
Which leaves the toaster chip, or, more importantly, the brake controller chip for my car, or the memory chip for my laptop, fighting for the scraps.
Fighting for scraps of capacity. That's exactly it. And this implies we could see, and in fact are seeing, shortages in the quote-unquote boring stuff simply because the exciting stuff is just too profitable to ignore.
This is a phenomenon you called crowding out.
We are already seeing it. It's called crowding out. And it is really the central theme of our deep dive today. We're going to map out exactly how this 0.2% of the market is distorting the reality for the other 99.8%.
We have a lot to get through. I think first we absolutely have to talk about the memory supercycle because that's the most direct result of this crowding out. And if you're planning to buy a laptop or a phone this year, you need to brace yourself because the price tag might genuinely shock you.
It is going to be a painful year for consumer electronics pricing, I think. A very painful year.
And then we need to dissect the battle of the titans, NVIDIA versus AMD. But I want to move beyond just the stock price conversation. I really want to talk about this shift to rack scale computing.
Yes, that's critical.
Because I think a lot of people still visualize a chip as this little black square you can hold in your hand. But what these companies are selling now is the size of a refrigerator.
And it weighs as much as a Honda Civic and needs its own plumbing. The engineering shift to rack scale is, you could argue, more important than the silicon itself right now.
We'll definitely get into the physics of that. Then we have the edge AI PCs, physical AI. Is it all just marketing fluff, or is there a real reason to upgrade your machine?
The billion-dollar question for Dell and HP.
And finally, the invisible hand guiding all of this. Geopolitics, tariffs, and the one thing nobody can ignore, the power grid.
The power grid is the ultimate boss fight for the entire AI industry.
It really is. So let's start with that market paradox, that 0.2% versus 50% number. Let me play devil's advocate for a minute here.
Go for it.
If the AI revenue is so massive, $500 billion, doesn't that money eventually trickle down? If NVIDIA and AMD are printing billions, doesn't that fund bigger, better factories that eventually help the budget sedan market too?
In a normal economic cycle, yes, absolutely. That is the classic trickle-down technology theory.
Right. The features in a Mercedes S-Class today end up in a Honda Civic 5 years from now.
Exactly. But this is not a normal cycle. This is something different. This is a platform shift. And the capital expenditure, the CapEx, being poured into AI is so specific, so highly specialized, that it doesn't translate easily to these other sectors.
How so? A factory is a factory, isn't it? A clean room is a clean room.
Not anymore. Not at this level.
Right.
The packaging technology, for example, that's required for these AI chips things with names like CoWoS, chip on wafer on substrate, it's a completely different universe from what you use to package a standard mobile phone processor.
So it's a different tool set, a different production line.
A different everything. So when TSMC spends, say, $10 billion building a new facility just for AI packaging, that facility cannot easily pivot to making chips for Ford or GM if the AI demand suddenly dries up. It's a one-way street.
So they're digging a moat that they can't cross back over themselves?
That's a great way to put it. They are locking in their infrastructure for a very specific type of compute.
Yeah.
And you just have to look at the stock market to see the reflection of this.
The concentration is wild.
The top 3 chip stocks now account for something like 80% of the entire semiconductor market capitalization. Is the definition of a winner-takes-most dynamic.
That concentration, it honestly terrifies me. From an investment perspective, from a supply chain perspective, you're basically betting that Google, Microsoft, Amazon, and Meta will keep spending tens of billions of dollars every single quarter, forever.
It's a huge bet.
What happens if they just stop, or even just slow down?
That is the multi-trillion-dollar question, isn't it? We are currently building all of this hardware on the promise of future software revenue. We're building the railroads before we even know if anyone wants to take the train.
Or before we know if there's actually a town at the end of the line worth going to.
Right. And if we get to the end of 2026, or maybe into 2027, and these massive AI models haven't generated the productivity gains or the new revenue streams that justify building a $100 billion data center, the pullback won't be a gentle correction.
No, it'll be a crash.
It'll be a crash. because the supply chain has absolutely no diversification left. They've put all their eggs in one very, very expensive basket.
And the lead times are brutal.
The lead times are the killer. These factories take 3, sometimes 4 years to build. So right now, in February 2026, we are pouring concrete for demand that we hope exists in 2029 or 2030. It's a high-wire act without a net.
Okay, so let's talk about the most immediate consequence of this high wire act for our listeners. Let's talk about the memory supercycle.
This is where the rubber really hits the road for the average person.
We've heard the term supercycle before in the memory space. It usually means prices go way up, then they crash spectacularly. But this one feels different. It feels like it's driven by a fundamental technology shift.
It is. It's all being driven by HBM high bandwidth memory.
HBM is basically the high-octane fuel for the AI engine.
You cannot run a large language model efficiently on standard memory. It is just too slow. The bottleneck is too severe.
Okay, let's break that down for a second. Why is standard memory too slow? I have DDR5 RAM in my PC at home, and it feels pretty fast to me.
It's fast for loading a video game or opening a spreadsheet. But you have to think about how a computer works at a physical level. You have the processor, which is the brain, and the memory, which is the library where all the books are stored.
Right.
In a standard PC, they're neighbors on the motherboard. To get a piece of data, the brain has to send a signal down a relatively long copper wire to the library, find the right book, and then drive it all the way back to the brain. We call that the commute.
The data commute.
Yeah, exactly. And in the world of electrons, that commute takes time. And crucially, it takes energy. For AI, where you're not just getting one book, but you're trying to move the entire library every second, that commute becomes an impossible bottleneck. It's like trying to fill a swimming pool through a drinking straw.
So the straw is the problem. What does HBM do to fix that?
HBM basically eliminates the commute. It gets rid of the neighborhood. Instead, it builds a skyscraper of memory chips, stacking them vertically, one on top of the other.
So literally stacking them,
Right.
like pancakes.
Literally like a microchip skyscraper. And then it places that skyscraper right next door to the processor. They're practically touching. And it connects them with thousands of tiny vertical elevators called through silicon vias, or TSVs.
Wow. So instead of a 2-lane highway between the brain and the library, you have a 1,000-lane elevator system going straight up.
A perfect analogy. And that allows for just massive, massive bandwidth. That's why it's called high bandwidth memory. But here's the catch. Building a memory skyscraper is incredibly difficult and expensive.
And it's getting even harder, right? Because in 2026, we're in the middle of this huge transition from HBM3E to the next generation, HBM4.
And HBM4 is the big leap. This is where it gets really revolutionary. I was reading about this, and it seems like the memory is starting to do more than just remember things.
This is the part that is really going to change things. With HBM4, for the first time, we're seeing the integration of logic directly into the base of that memory stack.
Yeah.
Logic in the memory. So the library isn't just storing books anymore. The librarian is actually reading them and summarizing them before sending them up the elevator to the brain.
That is a brilliant analogy. Yes, that's exactly it. It's a concept called processing in memory, or POM. By putting some simple computational logic at the bottom of that memory stack, you can do basic tasks like math or sorting or filtering right there inside the memory unit itself.
Which saves the main processor, the brain, from having to do that menial work.
It saves the brain from doing it, and more importantly, it saves the incredible amount of energy it takes to move that data back and forth, just for a simple calculation. It's all about efficiency.
It's always about efficiency and power.
But just think about the manufacturing complexity for a moment. You're now asking a memory company, a company like SK Hynix, which is the leader here, to manufacture logic chips. That's not their expertise.
Right, they make memory, they don't make CPUs.
It requires a whole new process, something called hybrid bonding, where you are literally fusing copper directly to copper at a microscopic level with no solder. It's incredibly precise.
That sounds wildly expensive.
It is. And SK Hynix is currently the king of this hill. They have reportedly sold out their entire HBM4 capacity for all of 2026.
For the whole year. It's February.
The entire year's production is already spoken for. If you're a data center operator and you didn't place your HBM4 order 6 months ago, you're not getting it this year, period.
So SK Hynix is sitting pretty. But here's the problem. SK Hynix and Samsung and Micron, they only have so many factories.
It's exactly.
If they are retooling all of their most advanced production lines to make these incredibly complex, high-margin HBM4 stacks, what happens to the standard DDR5 RAM sticks that go into my laptop?
They stop making them. Or, to be more precise, they make a lot less of them. It's that crowding out effect we talked about in its
Hmm.
purest form. The wafer allocation, the factory time, it all shifts to the high-margin HBM, and that leaves a massive shortage of standard DRAM for the consumer market.
And when supply goes down and demand stays the same.
Prices go up, and not by a little.
Yeah.
We are looking at credible projections that consumer memory prices could jump 50% by the middle of this year.
50%. That is a massive, massive jump.
It is a shock to the system.
Mhm.
We saw some channel checks from suppliers suggesting that a high-end 64-gigabyte memory kit, something that might have cost you $250 in late 2025,
Okay.
could be selling for $700 by April of 2026.
So wait, from 250 to 700?
That's the projection.
That's not inflation. I don't know what that is. That's panic buying. That's scarcity pricing.
It's pure scarcity pricing. And think about what that does to a company like Dell or HP or Lenovo.
Mm.
They operate on razor-thin margins for their laptops.
Absolutely. A few percentage points.
So if the cost of the memory in a $1,000 laptop suddenly triples, the entire bill of materials, the math, it just stops working.
So what can they do? Do they just eat the loss? Or do they raise the price of the laptop to $1,500?
They will try to raise prices, but consumers might balk at that, especially when they don't see the value in the AI PC features yet. So the more likely scenario is something we call shrinkflation.
The classic grocery store tactic. The bag of chips is the same price, but there's more air inside.
Exactly. The laptop stays at $1,000, but instead of coming with 32 gigabytes of RAM, you now get 16, or maybe even 8.
So we're actually going backward in specs.
For the same price, yes. It's the invisible tax of the AI boom. You, the consumer, are paying for the data center's insatiable appetite for memory.
That is a genuinely depressing thought. My next laptop is going to be less powerful because ChatGPT needs to think faster.
In the short term, yes. That is the trade-off the market is making.
Let's pivot from the effect to the cause. Let's talk about the companies that are causing all this trouble. The Titans, NVIDIA, and AMD.
The ones of the appetite.
We just got the Q4 2025 earnings numbers for AMD, and looking at the transcript, they are doing a victory lap. And you can't blame them.
It's a well-deserved one. AMD has pulled off one of the most remarkable turnarounds in tech history. Remember, a decade ago, this company was on death's door.
People are writing their obituary.
And now, they're posting revenue up 34% year over year, hitting nearly $35 billion. And the driver for that growth is one thing and one thing only.
The data center?
The data center segment. It's the hero.
But they're still the underdog, right? In this space, NVIDIA is the 800-pound gorilla.
NVIDIA isn't just the gorilla. They're the gorilla. They're King Kong and they're Godzilla, all rolled into one. Their market share is dominant. But the market is growing so fast, it's so big, that even the underdog can become a giant.
So AMD's strategy isn't to kill NVIDIA?
No, not at all. It's to be the credible second source.
And why is being a second source so important in this market?
Imagine you're Mark Zuckerberg at Meta or Satya Nadella at Microsoft. You're spending billions, tens of billions of dollars on these chips every year. Do you ever want to be 100% dependent on a single supplier?
Absolutely not. That's malpractice. That supplier has you in a chokehold. They can set the price, they can dictate the terms, the delivery schedule, everything.
Exactly. You want competition. You need AMD to succeed so that you have leverage in your negotiations with NVIDIA. It's so important that the hyperscalers are actively helping AMD. They're assigning their own engineers to help AMD optimize their software and hardware just to keep the market honest.
It's like keeping a spare tire in your trunk, but the spare tire is made of solid gold.
And that spare tire is getting really, really good. AMD is making this big push to what they call rack scale with their new Helios platform. And this is a concept we really need to unpack because it fundamentally changes the definition of what a product is in this industry.
Okay, rack scale. I hear this buzzword all the time, but I want to understand the physics of it. Why can't I just buy an MI450 chip from AMD and plug it into my own server? Why do I need to buy the entire rack from them?
One word: heat. It all comes down to thermodynamics. These new AI accelerators, whether it's NVIDIA's Blackwell or AMD's MI450, they draw an unbelievable amount of power. We're talking 1,000 to 1,200 watts for a single chip.
Okay, for context, a powerful hairdryer is about 1,500 watts.
Right. So imagine a hairdryer running on full blast, but all that energy is concentrated into a piece of silicon the size of a drink coaster.
That's a lot of heat in a small space.
It's an incredible amount of heat. Now, put 72 of those hairdryers inside a single server cabinet. The heat generated is so intense that if you tried to cool it with traditional fans, just blowing air over it, the chips would either throttle their performance down to nothing, or they would literally melt within minutes.
So air cooling is dead at this scale.
Air is not a good enough conductor of heat anymore. We've hit the physical limit. You need liquid.
Water cooling, like for high-end gaming PCs?
Exactly, but on an industrial scale. You need coolant loops, a water glycol mix running through cold plates that sit directly on top of the chips. This requires plumbing. It requires manifolds and pumps and leakage detection systems. You can't just retrofit an old server room for this. You need a completely integrated solution where the power delivery, the cooling, and the high-speed networking are all designed to work together as a single unified system.
So AMD isn't just a chip designer anymore. They've had to become a plumber. They're an HVAC engineer. They're a power systems expert.
They have to be. The Helios rack is a turnkey solution.
Mhm.
You buy it, you roll it into your data hall, you hook up the water and the power, and you turn it on. That's the value proposition.
Yeah.
But it also means the barrier to entry for building a data center is now much, much higher. You can't just build a startup data center in your garage anymore.
Speaking of scale, I saw a mention in the notes of a 6 gigawatt deployment partnership being discussed between AMD and OpenAI. I had to Google what 6 gigawatts of power actually looks like.
It is a mind-bending number.
Hoover Dam, one of the biggest power projects in U.S. history, is about 2 gigawatts. So we are talking about a single compute cluster that consumes 3 times the total power output of the Hoover Dam.
It's a city-sized amount of power.
Right.
And the fact that companies are discussing this seriously shows you where the industry is heading. We aren't building data centers anymore. We're building compute cities.
But doesn't that just bring us right back to the software problem? If I build a 6 gigawatt compute city, I need a lot of people, or in this case, a lot of software users and applications, to pay the rent.
And that is where the big ecosystem battle comes in. For a long, long time, NVIDIA had this incredible moat with their software platform, CUDA.
It's the only language AI developers spoke for years.
It was the default. It was the standard. But when you start talking about deployments this big, a 6 gigawatt deployment, companies are suddenly very, very incentivized to learn a new language to avoid that single vendor lock-in.
And this is AMD's software, ROCm.
It's ROCm, but it's also about supporting the open source frameworks like PyTorch and Triton. The goal of the industry outside of NVIDIA is to make the hardware underneath invisible. You write your code in PyTorch, and it shouldn't matter if it runs on an NVIDIA chip or an AMD chip.
If they succeed at that, NVIDIA's moat gets a lot shallower very quickly.
It does, and that is AMD's long game. They don't have to beat CUDA head-to-head. They just have to make CUDA irrelevant by supporting the open standards that everyone else wants to use.
Let's move down from these massive city-sized clusters to the device that's probably sitting on your desk right now. Let's talk about the edge.
The brave new world of AI PCs.
Every single commercial I see now is for an AI PC, Copilot plus PCs. The stats say they're going to be over 50% of the market by the end of this year. But let's be real for a second. Is this just a new way to get me to buy a new laptop? Do I actually need an NPU?
If you ask the average consumer on the street right now, the answer is a resounding meh. The surveys on this are brutal.
I can imagine.
Something like 43% of buyers say they don't even know what an AI PC does, and 50% say they flat out don't see the need for it. They just want to check their email and watch Netflix.
Does it have a headphone jack? Is the keyboard good? That's what I care about.
Exactly. And then when they see the price tag, which is inflated by that memory cost we just spent all that time talking about, they're just walking away. But here is the secret. In the short term, it doesn't matter what the consumer thinks.
How can it not matter? They're the ones buying it.
Because the corporate refresh cycle is dictating the entire market right now. We are rapidly approaching the end of support date for Windows 10. So IT departments all around the world, at Fortune 500 companies, hospitals, government agencies, they have to upgrade their entire fleets of laptops for security and compliance reasons. They have no choice.
And what are Dell and Lenovo and HP selling to them?
Only AI PCs. In the enterprise space, you basically won't be able to buy a new high-end business laptop without a neural processing unit. It's forced adoption driven by the enterprise.
But is there a genuine benefit for the corporation? Or are they just getting fleeced too?
No, for the enterprise, there's a genuine, tangible benefit. And it comes down to two things: privacy and cost. This is where the NPU, the neural processing unit, really shines.
Okay, so explain the NPU. How is it different from the CPU or the GPU that I already have?
Think of your computer like a construction site. The CPU is the project manager. It's smart. It coordinates everything. The GPU is the heavy lifter. It's the crane that moves all the big bricks. The NPU is a specialist. It's a guy who only does the electrical wiring, but he does it 100 times faster and more efficiently than the project manager could ever hope to.
And the electrical wiring in this analogy is AI math, specifically matrix multiplication.
Exactly. It's designed for one job.
Ah.
So if you run a local AI model, like a document summarizer or a real-time translator, during a video call on the NPU, it uses a tiny fraction of the power that the GPU or CPU would.
Which means your battery lasts a lot longer.
Your battery lasts longer, which users love. But more importantly for the corporation, the data stays on the laptop. It never goes to the cloud.
That's the privacy angle. That's huge.
It's the whole game. If you're a law firm, you do not want to upload your clients' confidential contracts to a public cloud service like ChatGPT. You want a local AI to summarize them securely on your device. The NPU makes that possible in an efficient way. So for the enterprise, the AI PC is actually a security product.
That makes a ton of sense. So the consumer buys it because they have no choice during the refresh, but the enterprise buys it because it solves a real liability problem for them.
Correct. And we're seeing a very similar dynamic play out in the industrial sectors, what we call physical AI.
This is the world of companies like NXP and Texas Instruments. They aren't making chips for chatbots.
No, they're making chips for robots, and for cars, and for factory automation. This entire sector was in a pretty deep slump for the last 2 years. There's a huge inventory glut after the pandemic. But in 2026, it's finally stabilizing. And the definition of AI here is very, very different.
It's not generative AI. The factory robot isn't writing poetry about its existence.
God, I hope not. We do not want the factory robot pondering the meaning of life. We want it to be predictive and reactive. We want it to look at a conveyor belt moving at 50 miles per hour, use computer vision to spot a microscopic scratch on a product,
And do what?
and use a precision air jet to blast that defective product off the line, all in the span of 3 milliseconds.
And it can't ask the cloud for permission to do that. The latency, the delay would be way too high.
Exactly. If you have to send the video feed to a data center 1,000 miles away and wait for an answer, the defective product is already in the shipping box. The decision has to be made right there, at the edge. That is physical AI. It's unsexy, it's invisible to most of us, but it drives the real economy.
And it drives the demand for all those boring chips we were talking about at the beginning.
Which brings us right back to the central supply chain problem. If a company like NXP needs more factory capacity to build these critical industrial AI chips, but TSMC is busy making multi-$1,000 Blackwell GPUs, you see the tension.
It all connects. It's all one big constrained system.
Yeah.
Now, speaking of tension, we have to talk about the geopolitical layer, the tariffs. On January 15th, 2026, a new 25% tariff on advanced semiconductors went into effect.
This was the headline that really panicked the market last month.
And you can see why. 25% is a huge number. If you just slap a 25% tax on a trillion-dollar industry, that's a recipe for massive inflation. But you told me before we started that the barks is worse than the bite here.
It is. When you actually read the text of the trade policy, not just the headlines, it's full of what we in the industry call Swiss cheese logic. It's full of holes.
Okay, give me an example of a hole.
Well, there's a huge national security exemption. So if a chip is deemed critical for the defense industrial base or for critical infrastructure, which you could argue almost everything is these days, it might be exempt, then there's a supply chain build-out exemption. If you're importing chips specifically to build out a new factory in the U.S., you probably don't pay the tariff.
So that $31 billion cost estimate that was floating around in the press
Is probably closer to 4 or 5 billion in reality. It's more of a strategic signal. It's the government's way of saying, please build your next factories here, rather than it being a pure tax grab.
Yeah.
But it does add friction. It means every chip company now needs to hire an army of lawyers just to navigate the bureaucracy and prove they qualify for an exemption.
It's a full employment act for trade attorney.
It always has been, and it always will be.
But even if we navigate the lawyers and we build the new factories and somehow we solve the memory shortage, we eventually hit the hard wall of physics. We hit the power grid.
This is the constraint that keeps me up at night. This is the real one.
We talked about that 6-gigawatt OpenAI cluster. But looking at the broader projection, the total demand for data center power could grow 30 times by 2035.
30x. Just think about the grid that we have today in most developed countries. It's old, it's creaky, it takes on average 10 years just to get the permits to build a new high-voltage transmission line. We are trying to push a tsunami of new electron demand through a garden hose.
So, what happens when the irresistible force of AI demand meets the immovable object of the public utility grid?
The geography of the internet itself changes. For the last 20 years, we built data centers near big cities because we wanted low latency. We wanted to be close to the fiber optic hubs.
Right, close to the eyeballs.
Now, we don't care about the city. We don't care about the eyeballs. We care about the power plant. We will go to where the power is.
So, we go to where the power is trapped, stranded assets.
Exactly. We will see massive new data centers being built in the middle of nowhere, right next to a hydroelectric dam or a nuclear plant or a huge solar farm, just to bypass the transmission grid entirely.
They'll plug directly in, behind the meter.
Exactly. And this completely shifts the power balance, pun intended to, companies that can provide efficiency. If you're a company like Texas Instruments and you make a simple power management chip that is just 2% more efficient than your competitors, you are suddenly a hero.
Because 2% of 6 gigawatts is a massive amount of money and energy saved.
It's a fortune. It's not just about computing faster anymore. The new race is about computing cooler and more efficiently. Watts are the new currency in Silicon Valley. If you can save a watt, you can sell it.
So let's try to synthesize all of this. We're here, it's early 2026, and it really feels like a year of transition.
It's the year we find out if this whole massive bet pays off.
We've got the split screen reality. The data center is booming, but the consumer is getting squeezed by these higher prices. We have the memory supercycle making every new device more expensive. We have rack scale completely changing the engineering of a computer.
And we have this infrastructure being built at a pace that, frankly, defies all historical logic.
It really feels like we have successfully built a Ferrari engine, this
Yeah.
trillion-dollar infrastructure of HBM4 memory and Helios racks and Blackwell accelerators. It is an absolute masterpiece of engineering.
That truly is.
But right now, when I look at the software that most people are actually using, I have to ask, are we just putting that Ferrari engine into a go-kart?
That is the fear that haunts every executive in this industry. The hardware is at least 5 years ahead of the software. We have built the physical capacity to run something approaching artificial general intelligence, but we're mostly using it to summarize our emails and generate funny images of cats.
The software has to catch up. The applications have to arrive.
It has to. The ROI clock, the return on investment clock, is ticking, and it's ticking loudly. Investors have been patient for 2, maybe 3 years with this spending. They will not be patient for 5. We need to see applications that generate trillions of dollars in real economic value, not just billions in hype.
If that software arrives, this really is the beginning of the fourth industrial revolution.
And if it doesn't, then we have successfully built the world's most expensive and complicated space heaters.
A 6-gigawatt space heater. That is a provocative thought to leave you with. I want to thank you for coming on and helping us unpack this massive, complicated stack of information.
It was a pleasure. Let's check back in on those memory prices in 6 months.
Absolutely. And to our listener, thank you for trusting us with your time. Keep an eye on those rack scale announcements and maybe go buy that RAM stick you've been putting off now before the price doubles.
That's probably very good advice.
We will see you on the next Pro Ticker Deep Dive.